Okay, this is the 1.3 transformation notes. This is part 1 of them. Part 2 is already on Schoology as a PDF. So a transformation changes the position or size of a figure. Transformations can be applied to the parent function. So if we start with the parent function of using the absolute value, which is the V-shaped one, a couple of things that we want to remember about absolute value is the domain and range of the parent function. So the parent function formula is absolute value of x. The domain is from negative infinity to infinity. So as you're walking along the x-axis from left to right, you first come to an infinity sign, and then you get to an infinity sign. And then range, as we walk from the bottom to the top, the first thing you get to is the point 0, 0. This is the origin, and that is where your picture starts. It continues as you go up toward the y. You see that it also goes to infinity. Okay, so that's the important thing about the parent functions. It's important we understand that that is our starting point, and after that, we're going to do some transformations. So our first step is we're going to do a very bad lighting in here. We're going to do an equation in, and we're going to see what the graph is doing. So here's my graph. So we're going to go to a new document, and we're going to put in our graph. To type in the absolute value graph, you have to type in ABS and then whatever's inside the parentheses. So ABS X would be how you would do the absolute value of the parent function. So here's what the parent function looks like, and as you can see, it prints with the absolute value signs. Just so you understand, those are not ones, they are bars. Okay, so that's our parent function. Now we're going to compare it to absolute value of x plus 2. So we're going to push tab to get another function on there, and then we're going to push ABS, parentheses, and we're going to put x plus 2 in, and enter. And we see that it has shifted to the left 2 places, so that's what our new graph would look like. So what is our new domain? This one has shifted to left 2 by 2. Okay, and our domain hasn't really changed because it's still all real numbers, and our range in this case has not changed either because it's still starting at 0. The value of x has changed; it's 2, 0. But when we're talking about the range, we're only worried about the y value, so y is 0. All real numbers still applies because even though our point has shifted over, we're starting at negative infinity and going to negative infinity. Okay, so we're going to do tab again, and we're going to put in ABS, parentheses, x minus 2. And we see that the new one that is in black has shifted to the right by 2. Okay, so here's something to note. Notice that shifting to the left by 2, if it's inside the parentheses with the x adding 2, we actually are going the opposite direction than you would think. Positive usually moves to the right, but inside the brackets, inside the absolute value, it moves to the left. Same thing here. Minus usually makes us think go to the left, but we actually are moving to the right. All right, so I'm going to delete out these two. So we only have the parent function again. And now we're going to put in absolute value where the 2 is on the outside of the absolute value. So it's absolute value of x, parentheses on both sides of x, plus 2. And now we see it has moved up. So it's shifted up. Okay, do it again. ABS. Again, the -2 goes on the outside, and we see that it's shifted down. Okay, so clear out these. And now we're going to see what happens when we multiply the absolute value by a whole number, a number bigger than 1. So absolute value, we're going to do 2, and we have to put absolute value part of this on our calculator inside the parentheses. So ABS, and then we put parentheses X. That tells the calculator, I want you to do multiplication. And just to be on the safe side, I'm going to put times in front of that. So what does it look like it's doing? It actually looks like it has pushed in, so it's thinner than it used to be. So even though it looks like it's pushed in, we're actually calling that a vertical stretch because it's actually pulling it closer. It's pulling it top. So when you put in 1, you actually are going further up on the y-axis than you were before, because before absolute value of 1 was 1, and that would be right here. But now absolute value of 1 is still 1, but times 2 shifts it up to 2. So we're actually stretching the y's. So that's how you can tell the difference between a vertical stretch and a vertical compression, which we're going to use VS for vertical stretch for future reference. And it is stretched by 2 because the y's are being stretched twice as long. Okay, we'll do the same thing. 1 divided by 2 times ABS of X. And we see that it becomes much wider because for every 1 it's going over, it's actually only going up half as much on the Y scale. Every X that goes over, it's only going half as much up on the Y. So that is what we call a vertical shrink or vertical compression. Which is VC for shorthand. Okay? And then finally, we have one more equation to look at. So we can see what happens when we multiply any of our parent functions by -1. -1, the negative in front actually means -1 times the absolute value of X. And we see that the absolute value has not changed in shape, it has been reflected across the x-axis. Okay, so that is a visual version of it. Now we're going to do a quick shorthand on making sure that we know exactly what they are. If it's any function, then these will apply to all functions regardless of if it's a absolute value, a quadratic, whichever one. Hold on. So whatever your function is, if you put x plus h, the value of x plus anything, any number you choose, it will be shifted to the left that amount of numbers. So shifted h units is how we would call it. It's a translation, so it's actually just shifting, moving left or right, but not changing any sizes. If it's subtraction, we shift to the right, h units. If f of x is being added to some value, some constant, we shift up, k amounts, k units. And if it's subtracted from it, we shift down, k units. Okay, when we multiply our f of x, whatever function it is, by any any number where the number, the absolute value, is bigger than 1. So less than 1, absolute value of 1, -2 would be 2. 2 is bigger than 1, so that would be here. The negative part of it does something completely different to the equation, but this is going to change its shape. So dilations change shape. Translations shift. Do not change shape. Okay? So the shape is changed by vertically stretching. Vertical stretch, which means that the y's are bigger. Okay, the y's are twice as big, 3 times as big. Whatever the letter a is, what that number is, our y values from the original parent function are twice or 3 times or 4, so they end up being a bigger number. Okay, if it is a vertical compression, which is VC, our y's are smaller. So when you're looking at your absolute value of, say, 1/2, 1/2 times x, when you put in 1 for x, you get 1/2. So instead of being 1, 1, you'd have 1, 1/2 as your point. So it's actually short, not going up the y scale quite as fast. Okay, and then if you multiply your reflection by or your function by -1, you reflect across the x-axis. So this is -1 times your f of x. Okay, so that is all of the transformations, and we're going to practice those in class.